So we're in chapter 8, section 5, and periodic properties of elements. Now we're going to talk about certain properties. Well, there's going to be 6 different properties that says to learn and apply to these basic trends. And these properties are going to be atomic radius. That means radius means basically the radius of the atom, basically. Ionic radius, radius of the ion, which are charged, going to be charged atoms actually. And then on to the ionization energy, the energy for ionization, the metallic character, the electron affinity, and the electronegativity. So we're going to describe those throughout this whole thing. So there's 6 different things we're going to describe. And then I'll actually give you some notes that's going to be very easy to remember what to know about these. But let's go over these first. First of all, the atomic radius. That it says that atom is not a hard sphere whose diameter can be precisely measured. So the density of the electron cloud, remember it has electron cloud, decreases with increasing distance from the nucleus, but never really reaches 0. Thus, there is no definite boundary for the atom. So we don't really have a definite boundary. Even though atoms look like they have a definite boundary, they not necessarily do now, we found, because of the electron clouds, right? The size, and it varies with the environment. For these reasons, we cannot tell exactly where an atom ends, but we can obtain approximate measures. So, this is in the atomic. We're going to find some of the atoms are going to be, the radiuses are going to be larger than other of the atoms. So we'll look through the table and find out which ones seem to be larger and what makes a radius of an atom larger in one element more than another element, right? So it says we plot the atomic radii against the atomic number, and we note a periodic variation with the largest radii coinciding with the alkyl metals. So let's look how this goes. So here they plotted, because they were going across from, the period 1. Period 1 would be periods that, of course, go across, right? They're rows. So the period row, it looks like during the period row from the hydrogen to the helium, going from left to right, it's getting more. The radius are getting more. And here again, this is period 2, and we're going from left, or from basically going from left, the period 2 with the barium, this Li all the way through here, period 2, and you see how they're going, getting larger, the radii, as you go larger in period 2. Period 2, this is going to be across, so very much across. And so you can see how, when you look at here, hydrogen is on going to be on this side, helium, so the period goes up, and you can see how it's getting bigger, and this one's getting bigger, and this one's getting bigger, and how they're dropping in the midst of this. So these are the periods across, though. So basically, as you look in this, it says from left to right, you'll have a decreasing. So from left to right, you'll have decreasing. So here we go, from left to right. This is this one, left to right. Lithium's on left to right. It's going to be decreasing, which it does. Lithium's going to be on this side, and neon's on this side, so you have a decreasing. Sodium to argon. Sodium's going to be, of course, on the left, and then argon's clear on the right, and you'll have a decreasing. And then we'll have the transitionals. This has to do, the transitionals come down here, but we have potassium and calcium down here, and then we go, the traditionals kind of change here in period 4, go across period 4. We have another bunch of traditionals, period 5. As period 5 goes across, you can see how it gets less, and then period 6 gets less. So, and here is, this would be your periodic table, the way it looks, right? So the largest are going to be, as you go down the column, they'll get larger. Why? Because they're going to have more shells, right? So they get larger as they go down the column, And as you go from left to right, they get smaller. So as they increase the radius, the smallest are going to be at the top here. The smallest are going to be the top on this side, the largest on this side. So basically going down the column, they're going to get larger, but going this direction, they're going to get smaller. Okay, that's the way it looks on the periodic table. And that's basically what you need to know on that section is what makes them. Let's see, another question would be what makes them larger? Well, they become larger as they come larger this way because they're going to have more shells and more energy levels. They just become larger as you go down. But they decrease because of the ionic contact of the decreasing from left to right. They decrease to because of the increased nuclear charge or the increased positive charges. Electrons are pulled closer to the making them smaller as they go this direction. Okay? So all of that, let's go on to the next. Ionic radius, similar. Ionic radius, so what's ionic radius? So when a metal atom loses electrons in a chemical reaction to become a cation, that means it becomes positive ion, it generally loses the electrons in the largest end, resulting in an ion that has one less shell. And so basically if you have a positive ion, you're going to be smaller than you have a negative ion. If you have a negative ion on this side, it's going to be larger. So here's some pictures of the whole table, and you'll see the neutral ones are the purple. So the cations, when they change ions, you see are the yellow here. So this will change to 2 plus, 2 plus. These are cations, positive numbers. And these are the negative numbers, positive. 3 plus, 3 plus. These are all positive, real positive. Positive. And then these over here are negative ions, as you see. So what they're saying about ions, there's actually 2 rules about ions. And let's go down here and I'll show you. As a rule, here's the rule here, one rule here and one right here. As a rule, simple cations are smaller than neutral atoms from which they were formed. So these positive ones are always going to be smaller. They're going to be smaller in a diameter, I should say in their radius, than the neutral ones, okay? And then thus, if you go down here, simple anions are larger than neutral because they have extra electrons in their so they're going to be larger. So when you have extra electrons, that makes them negative because electrons are negative. Extra electrons, you're going to make them bigger. So if they have a negative, they're going to be bigger than the neutral ones, and they're also going to be bigger than the cations. So the cations, the positive ones are going to be the smallest, and then the neutral ones then in between, and then the negative ones are going to be the largest, okay? That's all about there. So let's go on to ionized energy. So what's ionized energy? Well, the ionized energy is the energy required to remove an electron. So here it is. The energy required to remove an electron from an atom. Here's some picture of an electron being removed. So you have sodium, and then it turns to sodium, a positive sodium, and a moving electron. So now you have sodium, and it says 2 positive. You have 2 positive, and there is moving electron. So this is the first level, and this is the second level. We're going to deal just with the first level in the midst of this. The second level causes more energy. So what are we looking at? We're looking at the energy of ionization. The energy required to remove 1 electron from an atom. Not too bad. Ionization means positive or negative, means they're an ion. They're either positive, negative ion. And that energy is the energy required to remove electron. When you remove electron, you're going to make it positive, right? So let's see here. The energy required to remove the first electron is going to be the first ionization energy. And the energy required to remove the second electron is the second. That's what we were doing down here. But we're going to deal with the first, right? If we compare ionization energy to the atomic number, we find that ionization energy is a periodic property. The periodic nature can be seen in figure 816. In general, the first ionized energy increases from left to right across the periodic table and decreases down. It's going to be opposite. It's actually going to be just the opposite as we found with the radius. So it's going to, we found that now, what was the last one, the other picture? Let's show the other picture. See how these are going. This is period 2 and how it's getting larger from left to right. Period 3 from left to right, larger. And then the transition here in period 4, it's getting larger, right? With the time as it goes from the period from the period on the left side to the right side. So let's look at the difference. Remember, this is going just the opposite. So basically, the radius and how large an ion goes is the opposite than what we find with the ionization energy. It's opposite. This is opposite. See how they're going the other direction. So it's getting, instead of getting smaller, it's getting larger, right? It was getting smaller with the radius, and now it's going to get larger here. So let's go on to the next page. Here's a picture of it up here. So here we have, it's going to decrease instead of increase, as we did with the radius. How large it was going, it's going to get smaller. It's actually the energy we're talking about. The ionizing energy is going to get decrease as you go down these columns. Down these columns, going to decrease, and it's going to increase going this way. Just the opposite of what we just had. And this is with the ionization process. So let's see. And then there are some exceptions here that they go over. I'm not going to go over that, but there are a couple exceptions to this. It also says, recall Hund's rule. Remember Hund's rule? It says that electrons tend to occupy orbitals singly unless forced to pair. So basically, electrons come in as single electrons. And then after they're single electrons, they might be forced to pair. And this causes more energy to pair. Remember we talked about lasers, how the photons, actually electrons, pair and make it very strong, So, but anyway, Hund's rule says you have to get for single ones first, and then until they're forced to pair. And that one's the old rule. We found that rule before. So now we're going to talk about which number? The fourth characteristic is metallic character. So what is metallic character? Well, let's find the definition of metallic character. Ability to lose, well, let's talk about metallic character first, about metals. Metals have the ability to lose electrons very easily, and they can be ionized and joined to cations, very easily too. And they have a low ionizing energy. It doesn't take much energy to make them ions. So they're used very much in electricity and everything like that because they conduct electricity because they're very low ionization. So they become ions and become charged very easily, is what you're saying. And that's the metallic characteristic, how they can be charged easily. And this associates metals with low ionizing because power. So metallic character increases as they go down and decrease as they go. So when you talk about this, you're going to have the largest, actually the same as we had with the radius, how large they were. You're going to have, as they go down these columns, they're going to get larger, and as they go towards from left to right, they're going to decrease. It's going to be opposite from the ionization. So, and this is their metallic character trend. So the largest ones down here are going to have the largest metallic character. As they go down, they'll go from small to large, smallest to large, small's at the top to large. And then as you go across, they're going to be more metallic over on this side, and they're going to decrease, getting smallest on this side. So this is exactly the same as we did with the radius. So I'm going to go over all of these, on a sheet of paper so you can see, because that's when you look, they're going to ask you these questions. You have to look up. You're going to look up where these are and see which one is going to be stronger metallically than the other by saying, is this was, you're going to take maybe one over here and one over here and say which one is more metallic. Of course, you're going to say this one over here. So they're going to ask you those questions. Electron affinity. Electron affinity is the amount of energy involved in adding one electron to a gaseous element. So you're adding electrons, in the midst of this. So adding one electron to a gas is energy released, making the ion more stable. When you release energy, it's going to make it stable. And when energy is absorbed, you're going to make it less stable. In general, nonmetals have more negative energy values than metals do. And large negative values of E have a greater tendency to form negative charged ions. So basically, in the midst of this here, it just shows you we have Mg here, and it's losing an electron, turns into the gas of ionized gas, and it's going to be 231 kilojoules per mole. And then here we have F losing the electron, and this is negative 322. So this chart here is just going to say whether they are positive or negative, or what the amount of energy it's going to be in getting rid of an electron, right? Electron affinity values, and here are some you can see over here. These are all positive values, and these are negative. These are negative. These are zero. Nitrogen is zero. These are negative, negative, negative. Then they have some positive values here and on to negative. So it's basically, just to remember, it's basically the amount of energy involved in adding one electron. So here's a picture of the electron affinity trend. So less negative down here, from less negative to more negative. Okay, that's what you need to know. Just like a diagonal goes right up, less negative to more negative. So less to more. So it's kind of a diagonal one. Bing. So it says, in general, nonmetals have more negative values than metals, and these are all metals over here. So these are more non-metals over here mostly, and these are metals, and they just go up there, more negative. So in general, nonmetals have more negative. Non-metals more negative. These are more metals, negative, and the trend just goes up to more. Okay. And that's just, remember, the electron affinity is basically that energy involved in adding one electron. Just to remember that. Going on to the last is electronegativity. What is electronegativity? So electronegativity is the chemical binding. Let's just read this, what it says. In considering chemical bonding, however, a more important property, negativity, En, the ability of chemically combined atoms to attract electrons to themselves. So basically you have chemical combined electrons. So ionization energy, that's when they become ions, apply to isolated atoms, but these are chemical bonded atoms, okay? Electronegativity is often measured using a relative scale called the Linus Pauling scale. And that's when he lived there in 1901 to 1994. And fluorine would be the most electronegative, and it has electronegative of 4. Similar to ionization energy, electronegative increases from left to right across the period, and decreases down. So let's look at the chart on that. It's this one here. So now we don't have this here, but we're going to have, this is getting more negative. This is totally different. But this is like we had with the going on with the ionization energy. It's going to be similar. It's going to be opposite from the radius one. So here's the increasing, that it's going from largest to smallest. See, largest at the top here and smallest at the bottom. If you're going down these columns, going across, it's going to increase. So, and decreases and increases this direction. That's electronegativity. So let me see here. Electronegativity of selected elements. So over here we have, remember we said, they said fluorine over here. Of course, these are not electronegative at all because these are basically our noble gases, which don't have a charge. So basically you're going to have fluorine, this chlorine and chlorine and all these, this column of number 17 having the highest electronegative of 4. Remember, see how it gets bigger, how we said it got bigger here? It's getting bigger. Over here it's going to be bigger. Well, it is bigger. These are going to be bigger. 4 going to be bigger. And then the small, tiny ones are going to be here. 0.7. So 0.7 of cesium down here at the bottom is going to be the smallest. And fluorine is going to be the biggest right here. So you see how they transition on the column. So let's go on. Let's go to the example here. We'll see here what they're going to have us do. For each of the following pairs, tell which has the larger atomic radius, the larger first ionization, the more negative, and the greater electron negative. So we have to go through each one. So since sodium and potassium are in the same group, and the atomic radii increase down, K is going to be larger. So anyway, you have to look on the periodic table and see where they are on the periodic table. And as you look on the periodic table, you can see with each one of these things. I kind of, let's see, I want to show you my notes here because I think that you need to put the notes next to where they are in the column. So if we took potassium and sodium, and you look, they're going to be clear over, as you remember, they're going to be clear over on the left. So since potassium, sodium are in the same group, and you'll look where they're at, let's look down here. Here's where they are. So if we have potassium, sodium, you'll see potassium is here, and our potassium is here, and sodium is here. And so you want to look at the radius. And so the radius is going to get increase as they get bigger. So the potassium is going to be larger. They ask you to be larger or smaller. Just which of the following, tell which is larger. Larger one's going to be potassium, sodium. The potassium is going to be larger because it's getting bigger on this side. Okay? And then if we look at the other one, is F and Al. So here's F and here's Al. And as the size would be, it gets smaller going this direction. And so the larger one would be F. Is that correct? Let's look on here. So Al has more shell, so it is larger than F. So being smaller. So as it goes this direction, it gets smaller. So F is smaller, Al is bigger. So that's just with the size of it. So now they also want to know that the ionization. Well, ionization is going to be just opposite than that. So when the ionization goes opposite, we're going to have sodium. Basically, we said sodium. We said potassium is the larger, and sodium is the larger ionization because it's smaller and holds its valence more tightly, it says. The electron affinity becomes more negative going up to a group. So sodium has the more negative. As you go up, you're going to have more negative. So, and sodium has the more negative EA2. And also electronegative decreases down a group, so sodium is more electronegative. So it's kind of like potassium is larger, but sodium has all of the other qualities in the midst of that. Now let's go for F and Al. That's what I was doing there. F and Al, we did the size already. So let's look. So Al has more shells, so it's larger than F. So here's Al and F, so it's going to be larger than F because it's down here, and it has more shells, so it's going to be larger. So, and let's see, F is smaller and has the larger first ionization, so it's going to be larger. F's going to be larger in energy, and the ionization energy, which it is. And F is less metallic than, so it's going to be F, it's going to be less metallic as you go through there. And then it has more negative. It's also, F also has, so F has all those other three, but the bigger one, Al has more shells, is bigger, but F has the rest. So this last one, calcium and bromine. Let's look on where they're on here. Calcium and where's bromine? Let's see. Oh, they're in the same period. Calcium and bromide on this side. So calcium and bromide in the same period. So going here, atomic radial decrease across the period. So calcium and bromine are in the same period. So calcium is going to be larger because maybe it goes, calcium goes from larger to smaller. So calcium is going to be larger. Bromine, being less metallic, has the larger ionization, and bromine has the more negative energy, and bromine has the greater electronegativity. See how it is? So anyway, that's kind of that's what we're going to have for questions, and each one we can go through, and I'll show you what I did for these as we go. So as I went for these, I went with these. I'll show these in the next video, in fact, because the next video we're going to go over the questions, and so I'll show you how to do these a lot easier. But you have to have your periodic table to look them up where they're on the table, and then you can tell which ones are, for each of the 6 different things. You could tell by looking on the table. Okay, let's stop there.